which students found a little bit challenging. And I've sent you this. I think I'm not, shall I answer this question, what module this is? This is economics for history students. Okay? So, this question, this part of an exam question, is basically asking about some bacterial growth. And I've emailed you the question, and it basically says the absorbance of a starter culture growing in exponential phase is 1.2 at 10 o'clock. And you require a 40 milliliter culture growing in exponential phase with an absorbance of 0.2 at 1 p.m. to start an experiment. This is actually a very, very typical problem. When you grow some bacteria, you usually want them in exponential phase. Why is that? Because in exponential phase, all the genes that the bacteria need are expressed at optimum level. And this is when bacteria are at their best. And this is what you usually want. So the doubling time for the bacteria under these conditions is 30 minutes. And the first question here is, what is the growth rate for this bacterial culture when there is a doubling time of 30 minutes? And we know that we can really easily calculate the growth rate from the lecture last week. We know the equation for the doubling time. So if I put here equation for doubling time equals, so what is the equation for the doubling time? What is the equation for a doubling time? Anyone? What do we know about this reaction, or what the growth of this culture? What do we know about it? What order is it? Let's start with that. Somebody put here ln2 over r. Is that right? ln2 divided by r, yeah, we are getting there. So we've got 3 comments, ln2 over r. And indeed, it is ln2 divided by r, and r is the growth rate. What kind of reaction do we have? What order is the reaction? What do you think? And how do you know that? What order reaction do you have? Somebody said first order. First, but there's a question mark, so not entirely sure, which is good, because obviously if everybody was absolutely confident with their answers, then there wouldn't be a point of having a lecture. Is it a first order? It's not a zero order. Good. Yeah, that's right. It is a first order. The people are correct. But why? Why do you know it is a first order reaction from this very limited amount of information that you have? Why is it a first order reaction? What do you think? Why is it not a zero order? Why is it not a second order reaction? Why is it not a 1.5th order reaction? Why do you know it is a first order reaction? Does anyone want to hazard a guess? Or do you want to talk to each other and try to convince each other that you know why it is a first order? Why is it a first order? How can you tell? Any ideas? Why is it a first order? Ln no units. Constant doubling time. Oh, I like this idea. Well, Ln never has units. Yeah? So, unchallenged growth. But how do you know that? There's unchallenged. There is something about the doubling time that I really like. The rule is, if something has a doubling time or a half-life, and that is given, so here 30 minutes, doubling time. This only makes sense. Doubling time, half-life only makes sense in a first order reaction. Any other order half-life or doubling time does not make sense. It's only first order where it makes sense. And yes, your answers are right. So straight line, well, or with a straight line, you need to say what you plot basically for a straight line. A reaction that proceeds at a rate that depends linearly on only one reactant concentration. Well, it could be still a different order. But if you tell me that this must be a first order reaction, because otherwise a growth rate or half-life would not be defined, I would be a very, very happy person when I mark your exams. And that's what you want. You want me to be happy, because if Peter's happy, you get good marks. Easy. Oops. Yeah, we are back. So now we can very easily calculate the R. We just rearrange this equation a little bit, and we get R equals ln2 divided by 30 minutes. What does that give us? What does that give us? Using the fingers? What do you get for ln2 divided by 30 minutes? And I actually want you to do that because this is exactly the situation that you will have in an exam. And then if you don't find the right buttons on your calculator, you are basically snookered. So practice makes perfect. 0.0231. One says minutes to the -1. The other one thinks it's bananas. Don't ever, 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 under any circumstances, forget your units. Yeah. So we have 0.0231 minute to the -1 or 1 over minute. Either way is good with me. So that's our growth constant. Okay, are you happy with that? It's not terribly difficult to calculate that. Now, what we need to do now is really, we need to try and understand for the next question. The next question basically is, calculate how much of the starter culture you need at 10 o'clock so that you can do the experiment at 1 o'clock. Now we need to really understand what this experiment or what this question asks us. It's a little bit like almost a detective story. When people come across these word problems, they all, very often they start to freeze. Oh my God, I have no idea what this question actually is asking me. And what very often helps, if you do a little sketch of what's going on. I give you a couple of minutes to sort of try and figure out what this question actually might be asking you. So please feel free to discuss that with people sitting next to you. What is this question asking actually? And you don't have to whisper, you can talk freely. I'm not listening. What is this question asking? Try to figure out, be a detective. The question basically says, how much of the starter culture do we need at 10 so that we can do our experiment at 1? What does this question mean? Okay, so here is the sketch that I would do. At 1 p.m. we want to have 40 milliliter of a culture where the absorbance, which is an indication of concentration, the absorbance is 0.2. That's at 1 p.m. We need to prepare this culture at 10 a.m. and let the bacteria just simply grow. Yeah? So we set up our experiment basically we set up the culture at 10 o'clock with a certain amount of bacteria, let them grow, and by 1 o'clock we have an absorbance of 0.2. Will our concentration of bacteria or absorbance at 10 o'clock be smaller or higher than 0.2? What do you think? At 10 o'clock?
Oh, sorry, lower.
Lower.
You mean at 10 o'clock would be lower than 1 p.m.?
Yeah.
Yeah.
Lower.
I think so, yeah.
You think so? Anyone who disagrees with that? Higher or lower? Up or down? What is the concentration of the bacteria at 10 a.m.? Do we know that? Lower, lower. You're absolutely right, because we have a growth. Yeah? So at 10 o'clock it's lower, then the bacteria grow, and at 1 o'clock they reach 0.2. And in order to set that up, what we have is a different culture here. I haven't specified what volume we have, but here the concentration of the bacteria is 1.2. And we take some of that and put it in here at 10 o'clock. How much do we need from this 1.2 culture actually to get started here, to get the right amount of bacteria in our 10 o'clock culture? That is basically what the question asks. How much do we need of this? How can we actually address this? What do we know about the whole thing? We know it's a first order reaction. Yeah? So we can write, for example, the equation for a first order reaction. Oh, 6 lots of doubling times. That's a very, very interesting approach. I like that. And I show you a shortcut that uses that in a moment. But I show you first how you would do that if it was, for example, 35 minutes of doubling time or 25 minutes of doubling time, because then you can't use that simple thing. But we will come back to that in a minute. Let's write down the equation for a first order reaction. A final equals A initial times E to the power of, do we have a minus or plus? Minus or plus? What do you think?
I'm guessing plus.
Plus, plus, plus because growth. Absolutely right. Yes? So we have e to the power of plus r times our T final minus T initial. We very clearly have a reaction of that type here that I showed you last time, where we have B or A or whatever, where it grows. You start with 1, you end up with 1,000. So we can very easily use this equation here. And now what we can do is, we can in a way argue that we have certain things that we know. A final, T final. A initial, T initial. What is A final? What would you say in this case is A final? What is A final? There's a question mark. The question marks are going. A final is exactly our concentration of bacteria at that time. So it's 0.2. What is the corresponding T final? What is the time where we have 0.2? Be careful. Think through it first. There are different views here. 3 hours, 1 o'clock. Yes, it is. What we have here, the corresponding time is 1 p.m. Yeah? You are not wrong with 180, but be careful with that in the first place. Okay, so we have this one here. What is our A initial? What is our A initial? We said it must be lower. It must be lower than 0.2. You said that, right? And some other people said that. Must be lower than 0.2. So 1.2 contradicts that. Question mark. 1.2 question mark. Just a question mark. Isn't that what we are trying to find? Absolutely right. This is exactly what we are trying to find. We don't know what the A initial is at the moment. So that's the question mark. Yeah? What is the corresponding time? The T initial. Sorry? It's 10 a.m. You're absolutely right. And with that, we can now plug in these numbers into our equation. Or rather, we can try and rearrange this equation. So we bring that to that side. Or no, we don't do that. We bring that to that side. And we have A initial equals A final divided by E R. Now we have 1 p.m. minus 10 a.m. How many minutes is that? How many hours? 3 hours. So it's 180 minutes. Why do we need it in minutes? Why don't we just simply can use it in hours? Units. It's probably going to be my nickname. 0.2 divided by E, and for R, for the growth rate, we said it is 0.231 minutes to the minus 1 times 180 minutes. Rate constant, yes, yes, absolutely right. You make me very happy with your comments. And what do you see? What happens to the units? They cancel out, look. Minute and minute to the minus 1, they cancel out. And it must cancel out. Why? Because we have that as an exponent. And an exponent, something to the power of some units, doesn't simply make sense. Anything in an exponent is the same as anything in a logarithm, and you can't have any units. So, A initial equals 0.2 divided by e to the power of 0.0231 times 180 . Let me see if I can do that in my head. Zero 0.2 divided by 63.9. Is that correct? Has anyone tried? Is that right? Are you impressed?
Very impressed. Lies.
Huh?
I'm saying lies. Lies. I don't believe it, sir.
You don't?
I don't believe it.
You don't believe it?
That 1 second.
Sorry?
I don't believe that for 1 second.
What?
Like you did that in your head, like what? What?
How else?
By, I don't know, calculator using the iPad over there, which no one could see. I don't know, maybe you had some. Yes! Maybe, I don't know, sir. I don't know. You did something, you know what I mean? You knew the answer, probably. You knew the answer.
You're not impressed.
I would be impressed if it was real, but I guess it's not. You know what I mean?
There's a very simple trick how you do that in your head, which I'm not going to tell you. Rainman, I wish. Shall I tell you the trick? Oh, I missed out a 0 here. Thank you. Thank you very much. Sorry. Okay, so we have 0.2 divided by, well, roughly 64, isn't it? And that gives us an absorbance of 0.0031. I don't even need to do anything because somebody says it already here on the calculation. So I don't have to try and impress you. So that is our initial concentration, 0.0031. That is actually our concentration of bacteria at 10 a.m. So, how much of this starter culture do we actually need? How would you do that? How would you calculate that? What would be your approach for that? You have all done it, this kind of calculation. It just looks a little bit different. If I don't call that starter culture, if I call this stock solution, does that ring a bell? Stock solution. Yes! C1V1 equals C2V2. So we have C1V1 equals C2V2. We want to have concentration 0.0031 and we want 40 milliliter of that. And here our C1 is 1.2. So all we need to do is V1 equals 0.0031 times 40 milliliter divided by 1.2. Which gives us what do we get? Practice the calculations. Why is absorbance the same as concentration? Well, in this case, remember the Beer-Lambert law. Absorbance is equal to concentration times the length of the cuvette times the extinction coefficient. So absorbance is directly proportional to the concentration, and we can use the absorbance, if you like, as almost a proxy for concentration. So we have 0.1 milliliter. The rest, the 0.033, that's for your birthday. So, at 10 o'clock, you need 0.1 milliliter of your stock, of your starter culture, put into these 40 milliliters, so that when they grow at 1 o'clock, you have your concentration, your absorbance at 0.2. Does that make sense, how we untangled this question? Now, I want to quickly come back to what people have suggested here. bacteria will double 6 times during the 3 hours. This is actually something that we can do a second way. So what we know is that we have 30 minutes doubling time. And we know that the bacteria grow from 10 a.m. to 1 p.m., which is exactly 3 hours. And as your colleague rightly argued, it is 6 doubling times. So they start doubling. By 10:30, we have double the concentration. By 11, we have 4 times. By 11:30, we have 12. $12.30, 32, 1 p.m., 64. So, what we basically want is A initial times 64 equals 0.2. That's our A final. That is what we want at 1 p.m. So therefore, it's very easy to find A initial. A initial equals 0.2 divided by 64. Which is pretty close to what we said here with this equation here. Right? That it is 63.9 and not 64, it's just simply due to rounding errors. And if you really want to know how I did that in my head, I just simply did the 64 and then deducted just a little bit for rounding errors. And Robert is your mother's brother. Bob's your uncle. However, this only works if you have really nice numbers. If I had given you a doubling time of 18.7 minutes, this approach doesn't work. This approach, with counting the doubling times, only works with nice numbers. If you don't have nice numbers, you have to go through the A initial equals A final divided by E R T final minus T initial. Does that make sense? Should something like that come up in the exam, just theoretically, you know how to do it, right? I'll see you next week. Enjoy.